So how do we make alcohols? Now you're going to notice as we do more and more organic chemistry that there's a lot of interrelationships between different groups. You might already remember we've seen this for the alkenes and the alkyl halides. You can make alkyl halides from alkenes via addition reactions. You can turn alkyl halides back to alkenes via elimination reactions. So a lot of relationships between different functional groups, and that's indeed the same for alcohols. We've already seen making alcohols from alkyl halides. You take an alkyl halide, react it up with hydroxide. Usually at the A level you say you want this to be dilute, because if you do it too much then you go all the way down to the alkene. So we'll say that. So alkyl halide plus dilute hydroxide makes an alcohol, just a straight substitution reaction, goes via an SN2 reaction, and that works for primary and some secondary alkyl halides going to the primary and secondary alcohols. There's also something we didn't discuss in the core alkyl halide module, but was there in the extension material, and that is that if you just take, for some alkyl halides, react it up with water, then you can turn that in the alcohol within acidic conditions, and that works for tertiary and some secondary alkyl halides. Now you can also make alcohols from alkenes, although again we didn't talk about this in the alkene core material. It was there in the alkene extension material. Essentially you can hydrate an alkene with water to just turn into the alcohol. Now notice I haven't put any conditions there, because the conditions depend upon how you're going to do it. If we do it industrially, then we take ethene, react it with water, stew it up at very high temperatures and very high pressures, and concentrated phosphoric acid as a catalyst, and we make ethanol. And ethanol, as we'll see in a minute, very, very important substance for many, many reasons, not just the fact that it's found in people's liquor cabinets. Now in the lab, we do things a little bit more delicately. React it up with water with a sulfuric acid catalyst or a phosphoric acid catalyst to get this species here, the alcohol there. Now I've put an R group on one of the alkene carbons to emphasize that this is an addition reaction. It obeys Markovnikov rules. It works best for tertiary, better than secondary, better than primaries, and it goes via a carbocation mechanism. So I trust you can imagine exactly what goes on if you think back to the alkenes. Here we have our little group here. H adds to it, making the carbocation, and then water comes along to put the OH on the other carbon. Okay, various issues associated with this. There are alternative syntheses, one that does Markovnikov, one that does anti-Markovnikov, because as soon as you have carbocations, as we saw in the aromatics, you can have carbocation rearrangements. But right now we'll just say that this is one way to make alcohols. Another way to make alcohols is by reacting alkyl halides up with either dilute hydroxide or with water. Now, of course, there is a biological way to make alcohols called fermentation. So if we take a sugar, mix it up with yeast, put it in a warm place, and it doesn't require oxygen, we make ethanol and CO2. So for example, take glucose, ferment that away, turns into ethanol and CO2. Notice here I've written ethanol, not C2H5OH, but C2H6O to make it more handy for balancing. If we look at glucose, we'll see where we've got 6 carbons, but carbons occurs in both of those. We've got 6 oxygens, but oxygen occurs in both of those. Hydrogen is the easiest to balance first, 12 on the left-hand side, so we need 12 on the right-hand side, so make 2 ethanols. So 1 glucose makes 2 ethanols. Let's see what's left. We've got 6 carbons here, we've used up 4 here, so there must be 2 CO2s, and let's hope that the oxygens balance out, because we've got nothing else to do, and indeed they do. 2 plus 4 is 6. Now ethanol, of course, is used for recreation, but it's used for so much more. It's a very important industrial chemical, but more and more it's been used as a biofuel. You see it added to the gasoline that gets put into petrol tanks at petrol stations and so forth. Now, biofuels are kind of interesting. They're renewable. They are carbon neutral in terms of the chemistry, and everybody, every country around the place can grow crops that can be turned ultimately into ethanol. So you're not relying on those few countries that have massive reserves of fossil fuels. Anybody can make biofuel. Trouble with it is that, of course, every little bit of biofuel you make, ultimately you're using up food stock. And of course, to grow food stock, you need fertilizer. So therefore, it's not resource neutral. You need those other resources available. And the infrastructure to make it is not carbon neutral. You have to carry it around, transport it around from the farms into the cities or into the plants. And of course, just to build the plants is not carbon neutral itself. So always good to think about greening of chemistry. There is no doubt that fossil fuels need to be replaced in many ways, and biofuels, of which there are two, bioethanol and then of course biodiesel, that we will discuss in a different module, very important alternatives.